Hello, we're going to do two optimization examples to help you out with reviewing this topic. The first example we're going to use is kind of a classic optimization problem. We have someone trying to cross a river and get from point A to point B. And their choices are to row some part of it and run some part of it, and the rowing is slower than the running. So the question is, should they go from A to C and then down to B, or from A to D and then down to B, or should they go straight from A to B? What's the shortest time? So for a problem like this, it helps to label some variables. So I would label from C to D as X. Okay. And the question is, so where should point D be? What's the optimal distance X? And it could be anywhere from 0 if we row straight across to C, or all the way up to 8 if we row straight to B. And we know this side is 3. So then we know this diagonal, the Pythagorean theorem. I am stuck on a very thick pin there. Is 9 plus x squared. Okay, and then this distance here is 8 minus x. Okay, so now we've got our variables labeled on the diagram. We can do some stuff with this. So we want to minimize the time because it says as soon as possible. So we're going to want to write a function for time. And if we remember kind of the classic distance equals rate times time. If we solve for time, time is distance over rate. So we can write a function for time. So the time as a function of x would be the distance that we're rowing, which is that square root of 9 plus x squared, divided by the rate of rowing, which is 6 miles per hour, and then the distance that we're running, which is the 8 minus x, divided by the speed of running, which is 8. So now we've got time as a function of distance, and if we want to optimize time, find the, in this case, the minimum, we would want to take the derivative. So let's see, if I take this derivative, derivative of the square root is 1 over 2 times that square root. And then I've got the chain rule for a derivative of the inside, which is 2x, and then that 6 is just hanging out in the derivative. And then plus derivative of 8 is 0, derivative of negative x is negative 1 over 8. So there's our derivative, the rate at which the time is changing. And if we want to optimize time, we would want to find when that derivative is either 0 or undefined. Those are the critical points. Okay, so if we set this equal to 0, what can we do? These cancel. We can move 1/8 over here. And I've got x over 6 square root of 9 plus x squared, or 4 over 3x square root of 9 plus x squared. So then I can square both sides. And then isolate the x. Let's see, that would be 7/9. All right, so we find the critical value is at 9 over square root of 7. And we're hoping that that's a minimum, right? That if you go to a distance of 9 over square root of 7 and then run the rest of the distance, that would give us the minimum time. But we would have to prove it. So when you're doing optimization, you're actually doing a proof is what you're doing. So how do we prove a minimum? We have a couple different tools, and we'll be going over some of them later this week. But one would be to just test all the critical points and endpoints. So let's make a little XT table. And I'll label this is the closed interval test is what it's called. is when you just test all the critical values and the endpoints, if it's a closed interval, and see which one is the, in this case, the lowest. So the critical points, the lowest value x could have would be 0. The critical value would be 9 over square root of 7, and the maximum x value would be 8. And so you would just try all of those values in the original function t of x. So I think, let's see. Oh, where's my Desmos? There it is. All right, so there we go. I've already put this in, and again, you don't have to justify in your proof anything beyond I made a table. So here are my values. So I would just write those values in my proof. So when x is 0, 1.5, when x is 9 over square root of 7, 1.33, and when x is 8, 1.43. So 1.5, 1.33, 1.43. Oh, and I just remembered we should do 3. So 1.331 and 424. Okay. So in AP style, you want to give answers to 3 decimal places. So then here's our x of t. So the 1.331 is the smallest of all those values, has an absolute minimum. On the interval from 0 to 8 at x equals 9 over square root of 7. And we just proved that by testing the endpoints and the only critical value that there is. All right, let me zoom out. You can appreciate that whole beautiful proof. So that's doing optimization with a closed interval test. All right. Make sure you note down if you had any questions while watching that example, and let's look at another. Okay, so this is another kind of classic optimization problem where we're minimizing a distance from a point to a curve. All right, so if we want to find a distance, the distance is, using the distance formula, x minus 0 squared, y minus 2 squared, because we're finding the point from 0, 2 to the point xy. And if we find the point xy in the first quadrant, we can just reflect it, and we have negative xy in the second quadrant. All right, and then we can do a substitution, so we get d as a function of x. This is x squared plus, and then for y, we would put x squared plus 1. And let's clean this up a little bit. So this would be x squared minus 1. If I square that, I get x to the 4th minus 2x squared plus 1, or square root of x to the 4th minus x squared plus 1. Okay, so I want to minimize that distance. Now this is going to have a nasty derivative because we'd have to use the chain rule. So one kind of trick you can use when you're optimizing is if I minimize the square of the distance, I'm also minimizing the actual distance. So I can set up another letter, maybe capital D, to just be the d of x squared. And I can minimize that, and it's actually, the algebra is much easier. So if I do that, then this is a lot of d's. This derivative is very easy. And I would set that derivative equal to 0 and solve for x. So let's see, factor out a 2x. So x is 0, where x is plus or minus square root of 1/2. So those are all the critical values. Now, in the last example, we did the closed interval test, but there is actually no maximum x, so it's not really a closed interval. So to show where the minimum distance is, the closed interval test isn't going to really be our best buddy here. So instead, let's see, I did this one earlier. Take a little peek. Don't mind me. Okay. So let's look at the behavior of the derivative on either side of this critical value. So when x is x is between 0 and the square root of 1/2, then 2x is positive and 2x squared minus 1 is going to be negative. So the derivative is negative, meaning the function is decreasing. And then if x is greater than the square root of 1/2, the 2x is positive and the 2x squared minus 1 is also positive. So the derivative is positive. Oops, that should be a 0, my bad. All right, so we just showed that to the left of square root of 1/2, the function is decreasing, and to the right of square root of 1/2, the function is increasing forever, because it just says x greater than square root of 1/2. So therefore, d has a minimum on the interval from 0 to infinity at x equals square root of 1/2. And let me just make sure I answered the question. So we want the point, so I guess we should find the y. And then y is 1/2 plus 1, 3/2. So distance is minimum at square root of 1/2, 3/2, and negative square root of 1/2, 3/2. And then I've answered the question, which is determine the points that are closest to 0, 2, and those 2 points with the symmetry. Okay, I hope that helped.